big challenge for quantum field theory that became unavoidable in the 1990s is that one had to develop different methods for dealing with strongly coupled field theories. And what I have in mind is quantum chromodynamics, but there are many other reasons. And for that reason, I taught this course in two parts. One is weak coupling Feynman diagram expansion, which is very useful in certain settings. And then the opposite end, the strong coupling, where what happens to your neighbors doesn't matter so much. You're kind of self-possessed. Potential is important, interaction less so. And I emphasize WKB method as the method to deal with it. And the problem is how this works out in practice is that I derived a formula. The formula says you're supposed to sum up over all solutions, classical solutions. And what does that mean? So I gave you one discrete example, which was one-dimensional chaotic chain of Bernoulli coin flip, but I'm sure it wasn't very persuasive or impressive. So I want to finish with the attempt to understand how to deal with the real problem and get you some sense why the progress is slow, and I'm hopeful there will be more in the future, but it really is kind of at the edge of what humans understand. And I'll give it slightly different spin. So, I would like you to solve the problem of, let's say, pore confinement by looking at the solutions of Young-Mills theory, classical solutions, and show that you can compute the spectrum of particles described by QCD. Now, currently, we have one version of this, which is called lattice quantum chromodynamics, and that's one of the reasons why I emphasize discretization and lattice. But it's not very satisfactory. It's hard work. You don't get a good picture of what are you actually describing. What we had to understand once it became clear that one should understand classical solutions, we had to develop some understanding of them for strongly coupled theories. And here's my version following Blake, both a beautiful artist and poet. So the grand scheme for somebody in theoretical physics like myself is to solve several problems which, in my opinion, haven't been solved yet. They're still outstanding. One is to understand the observed spectroscopy of particles in standard model, which has to do with Young-Mills theory and quantum thermodynamics. And I told you to describe the theory, you have to write its classical Lagrangian function, and it's very beautiful. A generalization of electromagnetism with some colors added. And it looks like electromagnetism, but it's not linear because gluons can couple to themselves. So that's one thing you would like to understand. And if you're doing it in this WKB approach, you should have some intuition what the solutions look like on a classical level. And then we have the methodology of using WKB approximations and their quantum corrections. So WKB is supposed to kind of get you to the leading order in quantum quantum mechanics, but then we have systematics of correcting for that if we need to do it. So this hasn't really been done. I mean, there is an important part. Some analytic solutions have been found on these equations already, again, in 80s, 1980s, 1990s. And they generalize notion of solitons in nonlinear fluid dynamics. Soliton is a structure that solves equations like Navier-Stokes, but it's a highly nonlinear solution and highly localized solution. It looks like particles. So in the quantum field theory, people found such solutions called instantons. Instantons because they're localized in space-time in 4 dimensions. So as far as you're concerned, you see them at an instant in time and they go. One thing that one learns solving nonlinear problems, I'll focus on Navier-Stokes because there we have a very good intuition, is that you can have lots of solutions, but actually, they're not all equally important. And in my opinion, instantons are totally unimportant, regardless of what my colleagues think. So these are not the important solutions, in my opinion. Now, you might not be interested in Young-Mills, you might be interested in gravity. And the similar situation happens in a gravity, but it gets a little bit harder. We do have some classical solutions in gravity, but we also know when we look, for example, at black hole merger, that there is something very turbulent going on. Lots of colleagues in gravity will tell you that stuff looks turbulent, but we do not have a description of that kind of thing. But we know that when gravity is very strong, the typical solutions are turbulent. We do not know this, and I'm ashamed to say this, but since I got to Georgia Tech, I'm afraid to get any graduate student involved in this because I'm not sure I can get them a job if they get a PhD in this. So, and I myself, as it will be clear, do not have the tools to be able to solve this kind of problem numerically. In gravity, I'm kind of more hopeful because lots of people understand you need to understand classically turbulent solutions. But the main thing one gets from these nonlinear solutions is that the nonlinear physics is quite different from linear physics because things don't add up. By our intuition, where we actually know what we're doing, which is in case of fluids, is that there is an embarrassing wealth of solutions, which I showed in that first figure, like clouds. There are infinitely many solutions. It's not, harmonic oscillators that will say us, you'll have to do this. How do you do this? So now it turns out, even when you go to classical cases that which are either Euler equations of 19th century or Navier equations from beginning of 19th century and Stokes mid-19th century, even when you have equations you understand very well and they describe things you can look at, because if you go on a 3rd floor in this building, you can see them on human scales. I mean, you can look at them in seconds, minutes, etc. It's quite hard, and it took us a decade or two to describe what I'll tell you today, what kind of intuitions we have about solutions of nonlinear space-time or partial differential equations. So in the rest of this bye-bye, I will focus on Navier-Stokes and on its very simple-minded brother called Kuramoto-Sivashinsky. So Navier-Stokes equations quite easy to derive in a continuum matter course. So the first part was done by Euler. So this term here, the time derivative of velocity is the second derivative in time of the position, so that's acceleration. And what happens is in Euler's generalization of Newton to continuous media, you understand pretty quickly that you only, when you have a piece of matter, a little block of matter that's moving in a fluid, its acceleration will have to do with force, like what Newton likes, and in fluids there are some forces that come from electrostatics, for the gradient of pressure and stuff like that. So that part is very easy. But you realize pretty quickly that you also have to have two parts to this. One is acceleration right here, but the other one is the fluid is in motion, and you have to also take care of this so-called convective part. I mean, it's just the full derivative, it's nothing fancy. What it does is it makes Navier-Stokes a nonlinear equation because it depends on the second order in velocity. And it turns out we don't know how to do this very well. And, we've been beating at it for at least 150 years by now. And we know some stuff, but the story is not finished. But if you don't know how to do this, you won't know how to do Young-Mills, because it's the same kind of class of space-time partial differential equations. And, they have nonlinearities, and we have to learn how to deal with it. So this has been done in many ways for many purposes. Some engineers and lots of physicists like to give up on these equations, and they say, they look complicated to me. So they're like, no, I'll do statistics, etc. And some of that's very fruitful, but that's not what you need to do field theory of nonlinear systems. You actually have to look at the equations as they are and try to solve them. And now, the key thought that's very subversive, the way we teach all this subject is very old-fashioned. It's Newton. We teach you there's a state of a system, there are equations like Newtonian equations, and stuff, evolves in time. Humanly, that's the right thing, and that's how to think about the world around it. But nobody in her right mind will say that there is a supercomputer in the sky that evolves these clouds. This is not what's going on. So what is actually going on when nature deals with these equations? There isn't a thing out there that says, give me Navier-Stokes equation. I go, and here comes the cloud. That would be totally insane. And, nature solved these problems with utter ease. For us, they're very hard. And actually, Newtonian straitjacket is not helping us in this. So try to give you some feeling how, you can get deprogrammed, hopefully, from thinking of evolution in time. And if you train those field theories, you have no problems because, we did all this Euclidean field theory and Gaussian field theory, and we never evolved anything in time. We just solve our problems by looking at partition functions and conditions that they have to satisfy. And evolution in time, for example, if you try to do a calculation of magnetic moment, Schwinger calculation, as an evolution in time problem, you can do it, but it's horrible and ugly and, not very smart. So, turns out that you might be, interested in mass of a proton or quarks or something. But I don't think you can do this without some kind of theory of turbulence, in the sense that by theory of turbulence here, I mean, an understanding of how to solve nonlinear equations. And this is classical. We think about it at least since 1880s very seriously. In this millennium, the progress in the theory of turbulence has been very impressive. New ideas, lots of new results. But it's an ongoing project, and we have it in fluids, but we haven't transported it to Young-Mills or general relativity. So I will give you some sense of how theory of turbulence works in the context of what we need for making into field theory on the level of WKB approximations and maybe quantum theory from then on. And that's an open project, and as you will see, I'm not ashamed I'm not able to do it. It's hard. First, what I'll do is I'll give you a very rapid kind of visual idea of what we know about solutions of Navier-Stokes equations in third millennium. And then I'll go to a simpler model. Instead of having 3 space dimensions at one time, I'll go to 1 space at one time. And it has applications in applied math, but it has an advantage that you will have very clear visualization of what are the solutions of nonlinear equations. And I'll tell you what we know about identifying turbulent solutions of real Navier-Stokes. It's no approximations. Start with equations, given geometry, solve it. It's actually insane. We solve it with velocity at every space-time point of the fluid, accurate if the container is size 1. We compute it to 10 to the minus 11. So we're doing this in angstroms and fermis where engineers care about 5%. But the reason why that had to be done is it turns out to understand turbulent, you have to understand exponentially unstable structures, and they're hard to control unless you have a good numerical resolution. So here is an example which you can visualize. It's called plane quet. We don't have that experiment in-house. We have a similar one. We have a cylinder going around. But my colleagues have built several of these machines elsewhere. So what you think of is, suppose you have a printing press with 2 rollers, big rollers, and between them there is a transparent sheet of plastic. And as you move these rollers, the top plastic moves this way and bottom plastic moves toward. So there is a wall, transparent wall that's moving away. There is transparent wall that's moving toward me. And this is in meters, this experiment, but separation is maybe in centimeters, a fraction of centimeter. So intuition is that if you understand, some part of this motion of the fluid in the middle of this large domain, you can think of it as an infinite thing which is infinite in this direction, that direction is confined between the 2 walls. So the field theory of that would have 1 infinite dimension in time, because I'm evolving this in time, but then you would have 2 infinite dimensions in space-time. So you can write some kind of partition function, and you have to describe how likely is any possible configuration of the fluid. Now, what the experiment does is, this kind of experiment, what you do is you start very slow, And what happens there is a classical 19th century solution where you move two sheets of plastic or two walls, infinite walls against each other. That's what's called plane quarters. The mathematical physicist who thought about it. And as you move them very slowly, the fluid close to one wall is glued to that wall, opposite wall glued to the other wall, and then the fluid moves in layers. And relative, their balance, so the friction is minimalized, energy loss is minimalized, and you get some very simple solution. It says in the middle, fluid doesn't move, and it kind of moves linearly. That's called, that's the 19th century analytic solution, which we have for many fluid geometries, not just different. But what you know is that if you start shearing more, then actually the fluid gets unhappy and it starts moving in ways which we call turbulence. So what's plotted here is, it's very hard to visualize three-dimensional volume where everybody's moving with three-dimensional velocity. So one good visualization is we take a mid-plane. So this guy is a mid-plane between the two walls. And if there is flow is laminar, nothing happens in a mid-plane, totally boring. But once you start, shearing this thing, there will be walls, etc., and they will have to move through the mid-plane. So you can use two coordinates of the mid-plane to say a little vector field, how fluid is moving. That's what this little lines are here. And you can use the color to say how is fluid going through it. So for example, blue means I'm moving basically with this wall. So this blue area, everybody is moving with the wall. And but the red area, I'm moving with the opposite wall. So it turns out that, fluid gets a complicated thing that parts of it are trying to be glued to this, parts of it trying to be glued to that. And you can simulate it very well on a computer and you can measure it experimentally. And, thing looks like this. So this is sort of a small volume cell rather than the big one I showed you. And what you observe is that there is some critical value of velocity of the top and bottom sheet, relative to the frame, beyond which the fluid does something. And, you see lots of patterns in it because every so often it looks like it's aligned itself. This would mean that two poles going like that, like that. Then it falls apart and goes on and on. And if you do numerical experiments with this, what you discover is it never settles down. And later on, you understand why it never settles down. But basically, this is kind of the simplest example of what you mean by turbulence. You have a fluid motion. It's Navier-Stokes. Everybody, there's no approximation. It's numerically vastly more accurate than what you need to do the simulation. And the thing never comes back. And, it's a form of turbulence. Turbulence is like cancer, as various people like. Lung cancer as opposed to throat cancer, this is the simplest thing you can do. And if you do this kind of experiments in different geometries like pipes and moving cylinders and other cases, you start realizing that, there are specific things that have to do with geometry of the object, and there are some very general things that you will recognize across many examples. So this example is not misleading, it's just an example. And the main thing you learn by staring at these examples is that after a while, if I tell you, you're a graduate student, you're simulated this stuff, and I ask you, what Reynolds number did you do the simulation at? You look at this picture and say, well, it was about 420. Wasn't 800? Now, how the hell do you know this, right? And the reason why you know this is after a while, you start recognizing the features that kind of show up in this turbulence. There are things that pop up. And as you change the parameters or geometry of the problem, it's different features show up. So one thing that's very typical of turbulence, and it's missed if you're only averaging and plotting log plots, etc., is that it's totally recognizable, just like the clouds are recognizable. You've never seen the same cloud twice in your life, but you know that this is a cloud and not a car. And the way you see it is that it has features, spatial temporal features that are there, even though in detail, this thing never settles down and it keeps going. So what you learn from any careful experiment or simulation, where you actually look at this, is that it has structures. And these structures are recognizable. And that says that if you're going to do a theory of this, you have to produce a catalog of structure, and then you have to tell me how likely the structures are. And that's exactly what we did when we defined our partition functions. We said, well, partition function, what is a partition function? You have some field, some structure. And the partition function says, for every structure that you give me, what's the probability of seeing it? So, seeing letter T in the sky is very unlikely, but seeing a cloud is very likely. They're both possible as solutions of Navier-Stokes. And, instantons are solutions, but it doesn't mean that they are likely. You have to give it a number, say how likely they are. So we have work cut out as field theories. We have to say what kind of solutions exist, and then we have to say, how important are they. So that's what I'm doing today. I'll just give you a sense how you deal with non-trivial numerical, and there's no way that anything here could be analytic. It's okay, nothing wrong with that. But how to understand them. So the first thing one always does in partial differential equations, in field theory here, first you try to find steady solutions, things that are solutions, but they don't change in time and they're similar, same various locations in the space. I think it's probably 1860s or so, this laminar solution that's written first time down. So there is a solution of Navier-Stokes in this case, where fluid is layered. And guys who are close to wall moving this way are very blue. That's calling their velocity, so-called streamer velocity. The ones who are glued to the other part, they're getting red, and ones in the middle are not moving at all. In this case, green is, I'm not moving. So that one is totally obvious. Everybody understands that solution. You can teach it on any level. Now it took until 1990s for applied mathematicians, fluid analysis, Nagata in Japan discovered this first, to find solutions that don't look like that and can be only described numerically.
Why did it centrally symmetric? like there's symmetry on the left and the right, right?
Yeah,
Is
so,
that because
you
of
know,
gravity or
once you
because
do
of-
this in detail, you start using this, some solutions have discrete symmetries like this one might have it, I'm not sure. Some don't, you know, you have all kinds of symmetries that if you take your block of fluid, you turn it by 180 degrees and reverse velocities, equations don't change and boundary conditions change. It's very important, and you need that to classify the solutions. So you need to do that as a first thing when you seriously start classifying solutions. You go to all symmetry subspaces, but a solution like this one, the two things about it doesn't seem to have any particular symmetry. Turns out, you know, it comes in there are 4 copies of it, which are all physically equivalent, but you know, doesn't have much of a symmetry. But what's striking about this solution is that you look at it and you say, but I've seen this solution. Because if I go back to this fluid and look at it, I actually see a thing like this. At some point it'll show up. Like this one, look at this, you know, and this one looks very regular. And now I look at the steady solutions. These are solutions that don't change in time ever. And indeed, you know, my turbulent flow came close to this one and to that one. In terms of clouds, it says, you know, this was, I don't know, cumulonimbus, and the other one was, you know, cirrostratus or something. I can actually give names to this, and indeed, you know, to give them names because they're numerically exact solutions, so that, you know, they could be identified. But it turns out, just looking at steady solution is already, you know, putting some markers in the state space of all possible field configurations, which are very suggestive. And, you know, you have to understand how weird this solution is. You have a fluid, and it's moving. You know, so this is the velocity of the fluid. It means if I put some, you know, coloring in it, it'll be transported. So, you know, this thing is doing something. It works like some kind of mixer. But the velocity field itself doesn't change. It's steady in time. It's probably crazy, but that's what nonlinear world looks like. It's full of crazy looking solutions. So here are a few more. So one of our graduate students, Jonathan Halker, postdoc John Gibson, found these things. And Halker is a Google engineer, you know, a few blocks away from here. So, you know, GAP, whoever is active in GAP, you have to ask him to come and give a talk about real life, you know. Well, talk to GAP people. It's crazy not to have him come. I mean, he's a really smart guy who decided he wanted to support the family rather than to be a theoretical physicist. So there he is. But, you know, after a while, this stuff, you know, you can see the glimpses of it in this chaotic solution I showed you, but it's looking really crazy. I mean, it's going like this and going like that and going like that. And it is a steady solution of Navier-Stokes. It's a very good solution, nothing wrong with it. But these things, and you know, on general principles of nonlinear dynamics, there is an infinite hierarchy of such solutions. These are the simplest ones. They go on forever. Now, you're interested in turbulence, but these are, you know, what do these guys have to do? They don't change in time at all. So how are they going to describe turbulence? Well, you know, there are markers in this world. And then at the beginning of this millennium, something totally incredible happened. So, you know, for us, it was a big deal that there are these kind of markers that describe something that is reminiscent of turbulence, even though it is, but it's numerically exact. Numerical exact means like I'm solving a fifth order polynomial, and I tell you these are the 5 roots. You say, I don't want to do this. I want you to write, square roots and cubic roots and something. I say, well, Galois says I can't do it, so this is it. In that same sense, these solutions are numerically exact. You just make sure that to any given accuracy, you have them. They're as good as fifth roots of polynomial, except now they're roots of 64,000 order polynomial because you discretize your fluid in some way or other. So these are, exact things. There are no assumptions made of any kind. They're just what they are. But then at the beginning of this millennium, I got it actually as a Christmas present. The preprint arrived, I think in 2001. And Kawahara, assistant professor in Kyoto, spent lots of time in a dark room clicking at the screen, and he found an exact periodic solution. So he found a solution that looks indistinguishable from what I showed you before. The thing does that and falls apart and does it again. But in 99.70, computational seconds, it's a loop and it starts again. It's periodic in time, and by boundary condition turns out also to be periodic in space. Now, you don't appreciate how impossible this is, and I never believed it would happen in my lifetime. It's like this. I'm here, I have a boomerang, and I want to throw it so it goes over this angle and comes back and lands in my hand. It's hard. Now, if you were kind of playing pebbles on a two-dimensional, marbles on two-dimensional surface, actually that's easier. And if you go to more than 3 dimensions, you find that the probability of boomerang coming back is strictly 0. It's as likely as, throwing a dart and finding that it's exactly 1/3 of the length of this whiteboard. Numerically, it's this set of solutions is so small that you can't find it. So now, this is in 60,000 dimensions. Numerically, you put it on a grid like 60,000 independent fields. And what Kawahara did is he picks 60,000 fields in such a way that after 99 seconds, they all came back. So this is like throwing a boomerang in 60,000. It should not be possible. But it's like invention of transistor. Once one person does it, the dam is broken and we can all do it. It is possible. And so it turns out you can do this. And here is example of turbulence, etc. One can map them out. And I'll go very quickly through this. But basically, we can start mapping up state space of this fluid turbulence, and we can draw trajectories in which, the equilibria we had before are isolated points, and these other solutions, we can track them down. And we can compare what they look like as a plumber's image of a fluid versus what it looks like when you look at the state space. And here is what happens when you look at carefully selected degrees of freedom, 2 of them, but representative out of 60,000 compared to the fluid turbulence, and you start making sense of it. So I just want to tell you, it is possible. We haven't done it for young mills. I would be very grateful if anybody wants to do it, but could not get any graduate student in good conscience to work on it. But I'm quite sure it can be done. And we are now able to start mapping out the state space of possible solution, classical. This is all classical, not quantum mechanics, which should be a backbone of quantum theory through WKB. So I will not continue this because this is just a proof of principle. You can solve 4-dimensional partial differential equations, nonlinear, and find exact solutions. And they're much more interesting than instant-on solution of SU2 quantum chromodynamics. They're very rich to have all kinds of interesting behavior. And now I'll switch to a 1-dimensional version. So instead of having velocity being 3-dimensional, I'll just say, instead of having x, y, z, let's just have direction x. And the velocity is, how am I moving in that direction? So that can be plotted as 1-dimensional function or 1-dimensional position. And that can be realized in experiment as flame fronts. So people who do experiments in combustion actually do this. They take a Bunsen burner, they take a ring of gas coming out at uniform velocity along the ring and ignited and burning in oxygen. And they study how the flame front flutters. And that actually is, important for people who like to burn stuff. And it has a name. Not very inspiring, but 2 people who wrote it down first. And it's like this equation, except there is only one velocity field that I can visualize easily. It's nonlinear in exactly the same way, gradient velocity, multiplying velocity. And then, there is forcing terms and dissipation terms, and I won't details what that looks like. And this is so easy to put on a computer that I use it occasionally as, the first nonlinear, Strogat's kind of nonlinear course that senior undergrads take here. And they can do this, they can simulate it. And what's being simulated here is on the horizontal axis is the position. So I have X coordinate. Then I use a color or heat map to say the velocity is +3, it's red, but if it's -3, it's blue. So that's what the color means, is velocity up or down. And then what I can do is I can do integration forward in time and map at every instant in time the state of the flame front. And I can look how it evolves in time. So vertical line is up. So now this has the property that actually is kind of good because people use this lots in money-making schemes like machine learning, etc. Whenever you see a picture like this, you'll say, this is a simulation of Kuramoto-Sivashinsky. And they all look like this. It's very easy. Now, they're all turbulent in the sense that any section I take, I try to compare it to any other section, it's different. So it's a snapshot, it's not a 3-dimensional snapshot, it's 1-dimensional snapshot. But it's turbulent in that sense, and you can quantify it. If you, for example, don't care about burning gas, but you are doing some kind of optical nonlinear optics problem, you might like a different equation, which is also nonlinear, but it's called complex Ginzburg-Landau as opposed to Kuramoto-Sivashinsky. You run that nonlinear equation, and you get something that looks totally different. And after you've done a few simulations, anytime somebody tells you, shows you two pictures, you say Kuramoto-Sivashinsky. Because look at this, it's so distinctly different from the other one. The shapes that you see are very much the consequence of the equation of motions that you put in. They're very different, they're different. So now you can see what your duty will be if you do this for Young-Mills, or if you do it in general relativity. You'll have to say, what shapes do I get? What are the patterns? What these solutions look like? So that's what I'll describe the rest of this. So now, the way this numerical simulation is done is that I typically take a finite interval in space, and because it's translational invariant problem, typically make it periodic. So actually, I'm simulating on a circle size. And then the time interval, to describe the field, I have to discretize it. So there is a circle with, let's say, 1,000 points on it. And to integrate it in time, I have to take sufficiently small steps so I can resolve these features. And maybe, these pixels that you see, that there might be the integration pixels. So your floor, on which you're doing this integration looks like a cylinder. Now, when you look at your equations, you realize, the way you solve these equations, again, you discretize. And the natural way to discretize is to go to the Fourier representation. So what Plashan gets, becomes momentum square, or Plashan to the fourth, becomes momentum to the fourth. If you have a nonlinear term, you have to multiply two Fourier series and convolve them and stuff like that. So the natural way you solve this equation is the way we formulated this course from the start. It's always done on a discrete grid. And in this case, discrete grid goes that way. We do simulations, they look turbulent in that sense that, there's some features on them, but they never repeat as the time goes on. They never come back. So let's turn it around. Let's make time periodic and space infinite. Just solve the equations on that object. And when you do this, it turns out, it's not trivial, but it turns out that Kuramoto-Sivashinsky equation has a solution which you start at the instant of time and you arrange everybody, you're just throwing a boomerang. And by the end, it comes back exactly. But turns out you can start and you can arrange your initial conditions at instant of time, evolve your equation numerically, and the same solution is a solution in space or time. So this is really property of space-time, it's not property. It turns out, we are used to all this thing in time, but when you solve PDEs, you don't know what, is this time or is this time? As far, it's a formal notion, right? It's psychological. The other thing you noticed is when you look at these problems, why do you recognize them? For example, you notice that here there's some kind of horseshoe, not good or, pulled it out and kind of shaded everybody else. And then as you look around, there's another horseshoe like this. And the reason why you understand that this is complex Ginzburg-Landau and not Kuramoto-Sivashinsky is that in Kuramoto-Sivashinsky, there are no such horseshoes. So you realize that there's some features which are small, but they're the building blocks of what you're doing. So now you have a theoretical way to think how this is going to work out. And let's sketch out. So when you have this small thing like this, when you cut it with scissors, it's not a periodic solution because what's on the left and on the right is just whatever it is. But what if you were able to take a little torus, so you take a small thing, it's periodic both in space and time, and find the solutions of this shape. Then you could use that solution to say, all the stuff that you find here, this is actually a close visitation to small solutions that I have in my hand, which is, numerically exact, etc. So whenever you have infinite translational symmetries in space and time, the natural thing to do is to explore it by larger and larger space-time periodic solutions, which in this case is, this Navier-Stokes thing. I just close it and I look at a torus. And then you look, what is the solution I'm looking for when I'm solving this equation? And the natural thing is to write this in Fourier modes because that discretizes the problem. And when I look at these equations, I discover that what I'm looking for is actually a high dimensional fixed point condition. So I'm looking for field at position, Fourier space position K at Fourier frequency L in time. And I'm looking for a set of such fields that every place satisfies the equation, which is in this case, came from Kuramoto-Sivashinsky. So it's some Laplacian terms, a nonlinear term. So all of these equations just look like fixed point equations of kind we've already solved. But now, we have it in this very general setting. And none of them require the way you think. You think I'm evolving in time, but no, what the Euler-Lagrange equations are saying that every point of space-time you have a condition. And nothing is evolving in time. You're just solving, this fixed point condition, which is a higher order than, fifth order polynomial, but that's what it is. There are 60,000 on this field, and they have to satisfy this. And you think that might be hard, but actually I have a very good guess what it looks like because I just showed you solutions that solve this. So I actually know what the shapes look like. So the problem of turbulence now is not that, the river goes down and it's wild. It's what is consistent with Navier-Stokes equation, and it has a compact support in space and time. So I have to enumerate these solutions. And it turns out, this is a technical remark, when you get started, you have no idea whether things should be recurrent in minutes or millennia or femtoseconds. But physics tells you that it finds out the smallest possible torus in space and time, which is consistent with your equations and has a solution. So physics, of your equations gives you space-time units. The clock is not decided by you, but it's decided by the equation itself. And the main thing, conceptually, is that what do clouds do? They satisfy Navier-Stokes equations in the following sense, in what we thought about when we were writing our field theory. I'm here, and it says if I'm 6 feet tall, I can grow to 8 feet. However, I have to look what the left guy and the right guy is doing and make sure that they're all balanced out locally. Everybody has to do that. They all have to, be in agreement. So the Navier-Stokes equations are not evolution equations. Mills equation are not. They just say that, every place in space-time, I have to be well-behaved and do the right thing. And that's how nature figures it out. I'm a molecule and there are other molecules jostling around. I don't care what happens a kilometer away. I just have to make sure that these guys and I are in harmony, and that's given by the balance equation, like Navier-Stokes equation. So the way this works is exactly how we ended up with WKB theory. For example, Navier-Stokes equation says if something changes a little bit in time and changes in space, then these changes have to be balanced and they have to satisfy it. They have to be, find an equation equals 0. What we have to do to find WKB equations or classical equations of motion, we have a torus, we have a field, and we have to make sure that this is satisfied every place. So numerically, this becomes an engineering optimization problem. We can measure how much misbehaved I am at every site, by measuring this value of this function. If it's not 0, it means that I haven't been good. And we can add up all the squares and minimize that function, and that gives us a solution. And you don't have to integrate the river going down the stream, you just have to solve it. So that's how we actually solve it. And here's an example. You make some intuitive guess, you put it in this optimizer, and you get an exact solution of Navier-Stokes. And when you look at it, everybody will say, oh, but this is not Navier-Stokes, this is Kuramoto-Sivashinsky, because I've seen this before. But this is now an exact, pretty complicated solution of Kuramoto-Sivashinsky. And what it has this little guys here, it has all kinds of details that my eye is using or my brain is using to recognize this form. So let's focus on them. So it's not just that we see a recurrent shape. We see some shape that, because it's living on space-time torus, when I go sufficiently far away, will happen again, and some location. But also, it has recognizable features. So let's make this recognizable feature into an alphabet. So I can give a name to any one of these patterns. I'm watching Pacific Ocean, patterns. Instead of giving you a terabyte of data, I say this is 273375. I'll give it a name. That can be done. You can look at solutions, and then you can look at pieces of solutions, and at every step you can solve them on smaller and smaller two-dimensional, in this case, space-time torus. And eventually you find that, one possible thing that this Kuramoto-Sivashinsky does is it wiggles. It's an exact solution locally, and this is the smallest possible solution you can have. And it turns out, this is now not mathematics, we're probably wrong, but as a first rough guess, Kuramoto-Sivashinsky solutions all consist of wiggles or nothing happening, steady states where nothing much is happening, or what's called defects, a thing that, I used to have red, blue, but now I lost a part of them, and that happens very quickly in time direction, so people call it the defect in the pattern. So now the claim is, not only can I find solution, but I can tell you what all the solutions are. I find the smallest ones, then I start gluing them together to get the bigger ones together. Example. So, here is a big example. I take a defect, I take nothing happening, I take a wiggle, and I glue them together very badly. you know, because I use just scissors to glue these things together. They don't belong together. So if I compute my minimizer function, that should be 0 if we have the solution, this has some value. Well, then I run it through my engineering optimization algorithm to decrease the value. And what it does is it produces exact solution in which all the pieces are identifiable. So, you know, I started by saying I want some solution, nothing happens here. That is, you know, a defect, inverse defect, defect, something, you know. Now I replace my alphabet of shapes by the actual shapes. I put them together, and then I run it through a program, and I find a solution. So now, what are these solutions like? You know, they are all doubly periodic solutions. What it means in space-time, if I go to very long time and space, you know, they're just like tiling the floor by doubly periodic things. They're called, you know, Bravais lattices in condensed matter physics, or you know, theory of two-dimensional, you know, SLB shifts, there's something gravity that will also look like that. And you know, each one looks different, but they're capturing more and more of a detail of what you see in turbulence. And you know, there's a hierarchy of them. And now, you know, the partition function is supposed to sum up over all these guys. And then there is a part that I did not get into in this course, is, you know, how do you make sure that having a small pattern is maximizing your answer and all this repeats which are not physical, not affecting anything, because, you know, the real Kuramoto-Sivashinsky doesn't look like any of those things. It's actually glued by different patterns. So here we are in 2024. So this took about 20 to 30 years from start to finish, this Navier-Stokes and Kuramoto-Sivashinsky. People on the third and fifth floor can do very impressive three-dimensional Navier-Stokes things that I don't want to report on now, but you know, so there is a progress and things are moving. And at this institution, we don't have quantum field theory, so we cannot, you know, have an effort on nearing fields. Maybe we could have an effort on gravity. That's all. And this is where we are now. So this is Bergman's seventh seal. The ninth is playing death. And the tools are in place. You know, and there is a whole body of tools that we built over the years. And the future is very bright because it's kind of clear what we have to do. But, and it's going to be beautiful when it happens. And, you know, every time you start doing it, turns out it's more beautiful and richer than what we expected. So this Navier-Stokes saga, you know, is very surprising. I mean, it's incredibly nicely organized in something that looks sloshy and horrible and turbulent. It turns out it's very nice, rigid structure hiding in what we call turbulence in this context. And I would love to see it in quantum field theory, but it's, you can see it took so much time to do it. Just, you know, you need very good applied mathematicians. You have to convince them to do something. If it's three-dimensional fluid turbulence, they'll do it because they realize that's important. They don't have time to do the problem that you want to do that something. But I think that's where, you know, one of the barely open horizons of quantum field theory is explore this path. Of course, you know, there are many other paths. incredible, rich, beautiful field. Supersymmetries and supergravities probably will die, but this will not. And that's it. I'm done.